Question number 8 from the Northern Hemisphere 2001 methods paper. So we have this graph, this is the rule for the graph, therefore f of x equals 2x minus x to the 3 on 2, just expanding that bracket out. Find the derivative. Since I don't have a calculator, it's going to be the derivative of that, which is 2, minus 3 on 2 comes down, x to the negative, so 1 on 2, and I could write that as 4 minus 3 root x on 2, or I could leave it like that. Either of them is acceptable. Okay, part B then asks, the tangent to the graph at point B is perpendicular to the graph of G. Okay, so point B must be about here, and I've got a tangent that touches at B, and it's perpendicular to this line. Well, I know that this line has a gradient of 2 because its rule is 2x. Therefore, if it's perpendicular, the gradient of this line is negative a half. And if I could find when the derivative is equal to negative a half, I'll find the coordinate of B. So I've got f dash of x equals negative a half. So negative a half equals this, 4 minus 3 root x on 2. Move the 2 over, negative 1 equals 4 minus 3 root x. So move the 3 root x over, 3 root x equals 5. So root x equals 5 on 3. So x equals 25 on 9. And the tangent to find the coordinates of B. Therefore, B is 25 on 9. And then I need to sub 25 on 9 into the original. And the original is this, or this, 25 on 9. So y will equal, so I've got 2 times 25 on 9, which is 50 on 9, minus, I'm going to split my 3 and 2 into a half and then cubed. So that's going to be 5 on 3 cubed. So 50 on 9 minus 125 on 27 times up by 3, 150 minus 125 on 27 gives me 25 on 27. Okay, so that's part B. That's the coordinate of B. Over the page, show the graphs of G and F intersect once, only at the origin. F and G, so this here, so I want to set these two equal to each other. And I've got to show that they intersect at the origin. So I've got 2x minus x to the 3 on 2 equals 2x. Correct? So I'm going to have the 2x's will sum to 0. So I've got minus x 3 on 2 equals 0. Therefore x equals 0. And then if I sub in 2 times 0, I get y equals 0. Therefore 0 and 0. I've got to prove that both x equals 0 and y equals 0 to prove that they intersect at the origin. So I've done that. Part D. Okay, Q, where Q is positive, point D, can be shown that, why didn't they just tell me that in the first place? 3Q and f of 3Q. Determine the values of Q for which the tangent of the graph passes through Q and has an x-intercept greater than 4. So the x-intercept has to be greater than 4 that way. Okay, so I could place my tangent here and the x-intercept will be greater than 4. Tick. I could place my tangent here, but I can't place my tangent here or here because the x-intercept is over here. So the first place that I can place my tangent is here at the turning point. And I know from a previous answer that the derivative equals 0. Did I get the derivative equaling 0? No, I didn't, but if I take the derivative, 4 minus 3 root x over 2 equals 0. 4 minus 3 root 2 equals x equals 0. 3 root x equals 4. X equals 16 on 9. So that's going to be 16 on 9. Therefore, that's the earliest point because that's going to give me a horizontal tangent. And then if I go bigger than 16 on 9, I'm going to have a tangent that will have an x-intercept greater than 4. So the smallest value that 3q can equal is 16 on 9. Therefore, the smallest value that q could be is 16 on 27. So I think my answer is so far 16 on 27 is the smallest value, but it can't equal it. The largest value that q can be is 4, because when BD is 4, my tangent will have an x-intercept which equals 4, which isn't greater than 4. So my upper limit for 3q is going to be 4. Therefore, q equals 4/3. Therefore, 4/3, not inclusive, is the values of q that will give the tangent at D having an x-intercept that is greater than 4, because I want the tangent to sit somewhere in this region in here and attach.